The $600 billion global semiconductor market acts as the foundational bedrock of all modern manufacturing. It is the precise equivalent of the 20th century steel industry. If a nation wants to build automobiles, telecommunications infrastructure, or advanced defense systems, they require a continuous supply of microchips. Because this supply chain is so deeply integrated into global output, a single localized shock can stall entire economies. During the manufacturing freezes of the COVID-19 pandemic, automakers and electronics manufacturers worldwide were forced to halt production, simply because the flow of these silicon components temporarily stopped. That fragility exists because production is constrained by severe geographic chokeholds. The capability to design, manufacture, and assemble advanced chips is highly concentrated among a small group of allied nations: the United States, Taiwan, Japan, and the Netherlands. Securing silicon is a critical sovereign defense mandate. Without these components, a nation loses control over its industrial base and the ability to maintain modern infrastructure. To eliminate this vulnerability, China is pursuing a strategy of technological autarky. Over the last decade, Beijing has invested over $100 billion to construct a completely closed-loop system, attempting to achieve absolute self-reliance across every single step of the semiconductor value chain. India has structured a radically different counter-strategy. Through the India Semiconductor, the state has allocated 76,000 crore rupees, roughly $10 billion, to build its own silicon infrastructure. Rather than deploying capital to build sovereign R&D from scratch, India uses its budget to subsidize foreign partnerships. The state provides capital expenditure subsidies, covering up to 70 to 75% of the costs, for global companies willing to set up facilities on Indian soil. To understand how this capital is deployed, we must look at the three distinct phases of the semiconductor supply chain that India must penetrate: chip design, fabrication, and ATMP. By heavily subsidizing foreign entry into these three phases, India's model explicitly trades the pursuit of total autarky for immediate access to established intellectual property and an accelerated entry into the global market. The value chain begins with chip design. This phase relies on highly complex electronic design automation, or EDA software. Today, the United States holds an iron grip on this stage, controlling roughly 70% of the global EDA software market. Yet, India already holds hidden leverage in this initial phase. Indian engineers currently make up 20% of the entire global semiconductor design talent pool. Major fabless technology giants, massive companies like Intel, AMD, and NVIDIA that design chips but do not physically build them, already rely heavily on these localized R&D teams in India to architect their microprocessors. With a foundation in design already established, India's next target is the physical supply chain. The most viable entry point is the final stage of production: assembly, testing, marking, and packaging, commonly referred to as ATMP. The function of an ATMP facility is to take fragile, raw silicon chips and encase them into usable, durable modules. This packaging gives the microscopic chip a physical body that can dissipate heat, process electrical signals, and physically connect to a circuit board. Setting up a primary fabrication plant costs between $20 and $30 billion. Building an ATMP facility requires only a fraction of that capital expenditure, significantly lowering the barrier to entry. The Indian government has capitalized on this specific economic reality. Of the first 10 projects approved under the India Semiconductor mission, 5 are dedicated entirely to ATMP facilities. For a developing nation, ATMP provides the most capital-efficient wedge to transition from a software and design hub into a physical exporter of semiconductor hardware. The true choke point lies in step 2 of the value chain: fabrication. This is widely considered the most complex manufacturing process in human history. Formidable structural moats surround fabrication. Taiwan manufactures over 60% of all chips globally, while a single Dutch company, ASML, holds a monopoly on the advanced photolithography equipment required to print them. To fabricate a chip, silicon ingots are sliced into bare wafers. Machines then etch billions of microscopic binary transistors onto that raw wafer using atom-thick plasma. Given this immense complexity, the global race is focused on achieving sub-5 nanometer scale for advanced AI computing. Yet the Indian government is intentionally subsidizing the production of older 28-nanometer technology. This chart visualizes the total addressable market demand for semiconductors. Chips that are 28 nanometers and larger are known as legacy nodes. While they lack the density of advanced AI chips, nodes 24 nanometers and above account for a massive 50% of total global market volume. These legacy chips are the critical components that power foundational industries. Telecommunications networks, electric vehicles, consumer electronics, and heavy defense infrastructure rely entirely on this specific node range to function. Capturing the legacy node market is a highly calculated defensive play. The immediate goal is securing domestic industrial resilience, rather than launching an offensive bid to win the global AI computing war. Fabricating even legacy nodes requires hyper-fragile infrastructure. A mere 1% fluctuation in the frequency of the power supply, or the physical vibration from a heavy truck on a nearby road, is enough to ruin an entire production batch. To remove these physical bottlenecks, the central and state governments are coordinating aggressively. They are executing land acquisition, stabilizing power grids, and clearing ultra-pure water permits in under 100 days. India is securing the expertise to run these highly sensitive facilities through strict joint ventures. Tata has partnered with Taiwan's TSMC, and engineering giant L&T recently acquired Fujitsu's power semiconductor unit to absorb their operational knowledge. Partnering with established global players serves a vital geopolitical purpose. It sends a clear signal to the West that India intends to integrate as a trusted node in the existing supply chain, rather than emerging as an isolated intellectual property threat. Beyond the cleanrooms and subsidies, there is an invisible bottleneck that dictates whether a fabrication plant succeeds or fails: the raw material inputs. The chemical requirement for a single standard production line is immense, continuously consuming over 500 unique chemicals and 50 specialty gases. These are not standard industrial materials. The purity standards required for semiconductor fabrication are measured and refined down to strict parts per billion tolerances. A single microscopic contaminant can destroy a wafer. Currently, Japan operates as the global hegemon in the production of these ultra-refined chemicals and materials. To ensure the raw materials match the capacity of the new fabs, India is utilizing direct memorandums of cooperation with Japan, actively transferring this legacy technology to localize the chemical supply chain. In response, large domestic chemical manufacturers like Deepak Nitrite and Tata Chemicals are already adjusting their capital expenditures to supply this highly specialized new ecosystem. Establishing a true semiconductor industry requires this deep backwards integration. Without controlling the basic chemical elements, a nation simply imports its dependencies under a new name. India's tactical loop is set. Anchor the industry with existing engineering and design talent, enter physical manufacturing through ATMP packaging, and subsidize legacy 28-nanometer fabrication through foreign alliances. The sovereign targets tied to this loop are aggressive. By 2030, the state aims to scale the domestic semiconductor sector into a $10 billion industry and capture 10% of total global consumption. However, India's entire $10 billion state incentive package is dwarfed by the incumbents. A single market leader like TSMC deploys roughly $40 billion annually on capital expenditure and R&D alone. This raises a central question. Can targeted subsidies, coordinated state-level permitting, and geopolitical alliances compensate for the overwhelming capital mass of existing global monopolies? India's trajectory in this sector depends on its ability to engineer itself into an indispensable manufacturing partner for the present.